Hi, I'm Nimrod from BDN Automotive, and today you're watching the very first episode of the BDN Combustion Analysis tutorial video series. By the end of this series, you will be aware of everything what is necessary to start analyzing your engine, to optimize its performance, optimize its efficiency, and more importantly, you can stay on the safe side and quantify knock, and you can draw your own measurable limit so you protect your engines from blowing up. In today's video, first of all, we will introduce you to the BDN CA-6 combustion analyzer, and after that we will go through all the important definitions and phenomena which are relevant to understand combustion analysis. So let's start with the BDN CA-6. This is the very first affordable and really user-friendly combustion analyzer on the market. It has 6 channels for pressure transducers and 2 additional for VR and Hall sensor for the trigger. It communicates over CAN, has an IP67 rated CNC machined housing, and Sorio motorsport connectors. Combustion analysis is measuring the pressure inside the cylinder on a very high frequency and visualizing it against the crank angle. The following parameters can be calculated for each engine cycle. For example, peak cylinder pressure, which is obviously the amplitude of the curve. Knock amplitude, I'll talk about it a bit later because this is a bit more complicated. Mass fraction burn function, this is a very useful one. If you take a look at the heat release function and cumulate it, normalize it, you will have an S-shaped curve, and which is going from 0 to 1. If you take the half of it, which is showing you the 50% of the energy has been released, that is the MFB 50 point. If mass fraction burn 50 is around 8 to 10 degrees after TDC, you will have an optimized engine efficiency and the highest performance. Last but not least, there is the IMAP, indicated mean effective pressure. This is related to the area under the pressure trace and is directly proportional to the engine's output torque. So let's get back to knock. During the combustion phase, the spark plug fires the air-fuel mixture, which starts to burn radially. As the volume of the combustion products are significantly higher than the unburned mixture, a pressure wave arises between the burned and the unburned zone. This wave then reflects from the cylinder walls, the pistons, and all the other mechanical components. Detonation, aka knock, occurs when an abnormal auto-ignited pressure wave collides with the normal one, creating a local pressure peak. The effect of knock could be monitored on the pressure trace as it is being overlaid as a pretty high frequency oscillation. In these 4 pictures, you can see a reference cycle on the top and a knocking cycle. On the left, there's a pressure trace. On the right side, there's an FFT analysis. In the reference cycle, you can clearly see that there is only one peak of amplitude, which is around the frequency of the normal engine operating points, so a couple of kilohertz. Whilst in the knocking cycle, you can see another peak, which is at 7 kilohertz. This is the nominal frequency of knock. It is important to say that knock is not always harmful. What we only need to know is the amplitude of it. As a rule of thumb, we usually allow 1 bar per 1000 RPM. So for example, if you have an engine revving at 5000 RPM, you can allow 5 bars of knock. What you usually record with an OEM knock sensor is not the pressure. It is some kind of noise, basically the knock sensor is a microphone. So you need to calibrate it with having a pressure trace like this. So you know you have a transfer function between the pressure amplitude and the level of noise, what you record with the knock sensor. So that you can wire into the ECU, and after that you will have a pretty accurate calculation. Make sure you subscribe to our newsletter in the link below to get all the relevant info and updates, and of course the next sessions of the BDN tutorial videos. Get the most out of your engines and let's win races together.